In this video, I'm going to go through some Edexcel past paper questions for D2 on the travelling salesperson problem. And it might be useful for other boards, but bear in mind that this might actually be on D1 for some other awarding bodies. So, first one's just a standard definition problem. Do read in preparation for your exam, do read through the glossaries for D2 and D1. Because you could be called for any definitions really that appear there, and maybe more, but definitely from the glossary that you will find in the syllabus for Edexcel D2. So here we have the answer to part A. It is a finite sequence of edges such as the end vertex of one arc is the start vertex of the next arc, I suppose. You should know also the definition, which comes up more often in D1, of what a path is. And there, for a path, you've got this extra constraint that you're not allowed to revisit any of the vertices where no vertex is visited more than once. But that doesn't exist here. So, for example, going on the one for the next example, these are all walks. It doesn't matter if I go to the start vertex, how many vertex I go through, whereas a path would need to not visit any other vertex more than once. So that definition for a walk is no constraint about going through the vertex more than once. Okay, now on to the definition of a tour, which in a sense is kind of essential when we understand the travelling salesperson problem. So here's the definitions for a tour. So a tour is a walk through a network which visits every vertex and returns to the starting vertex. I mean, it can visit more than once, but that's not a constraint. It can at least once, but we can just say every vertex is visited and it's a walk through the network. So for this example, which comes from 2, I can say that this is a walk. This is a tour because I started with, I can't remember where I started now, but I think I started at A. That was a tour. So long as every vertex, I'll try again because I've forgotten where I started there. There you go. There, that is a tour because we've gone back to our starting vertex. Okay, from A to C to B to D, F, H, G, E, and A is a tour. And in a sense, that's essentially what the travelling salesperson problem is all the time, because we're trying to find the minimum tour through a network such that every vertex is travelled at least once. Every vertex is visited at least once, and we return to our starting position. And that really is what the travelling salesperson's problem is all about. With the classical problem, we say that it's visited exactly once, not at least once. So but in any case, it is about visiting every vertex and returning to a starting position, and that's a tour. Okay, so let's move on to the second question. Past paper question, not sure which year. I certainly know it's from before 2010, because all of these questions will be. Hopefully, if you're going through the papers, you'll see this somewhere. First bit is the kind of thing you could get on D1, so we answer it in the same way. Obtain a minimum spanning tree using Kruskal's algorithm. So Kruskal's algorithm involves taking the shortest edge first. If we take the shortest edge, and we look for the shortest edge here, and you need to be very careful, but the shortest edge is GH. So GH is the shortest edge, 38. Okay, and then we look through the network for the next shortest one. And you need to be very careful. Some people actually list them all in order first, make sure they have all the edges first, which is an acceptable way of doing it. But if we look at it, it looks like GF is the shortest. I'm going around there and seeing 56. Yeah, GF is the shortest, and we carry on through the network like this. So the next one is presumably CA or AC, which is 57. Okay, and then The next one is looking at the next shortest. We've got 59 there. Is there any smaller than 59? I'm tempted to go for that. 59 is the smallest. That's CE 59. Okay, and then we're looking for the smallest after that. We've got 61 now. I'm just seeing if there's anything smaller than the 61. And we just add them as soon as, 61, FE 61. And unless it makes a cycle, in which case we reject it, we'll add this to our tree. Okay, now we can then look for the next smallest, CD, which is 64, and CB, which is 68. There were no rejections here along the way. We do need to show rejections. So for example, if we'd ever had one that created a cycle, we'd need that and just put a cross next to it. But in this case, we've got the tree is now complete because every vertex is included. So that's our answer to part A, only 2 marks. So that's presumably why they made it relatively easy and not problematic to work out. So then it says, use your answer to B to find the upper bound. Well, if we add all these together, we get 403. Adding all of these together comes to 403. So the lower bound is double that. Sorry, upper bound, initial upper bound, sorry, not lower bound. Initial upper bound is 402 times 403, which is 806. Now, when we think about why we're doubling it, just think about what the travelling salesperson is. We're finding a tour such that every vertex is visited at least once. So imagine we're starting on A here. Let's change colour for this purpose. I could go to A. We're going to use these edges for our network. I could go to A to C to B, but each one I'm going to have to go back on myself in order to get back to where I started. No, it's not. I've made a bit of a mistake there. Let's start again. I could go over here first. Doesn't really matter. But you'll see that every vertex is visited at least once, but that involves going along each of the edges twice, which is why we double it. That is a tour. And we have visited every vertex once by going along every edge twice, which is why we double it. Okay, so now we're now into the more kind of problematic, well, meaty parts of it, if you like. It says, starting from your initial upper bound, use shortcuts to find an upper bound which is below 630. Okay, so let me just draw this out here. I'll do it. Just go back to below here. So I'm going to make it a little bit similar to where it's coming from in the network, but not draw on the network above because there's too much going on there. GH, F, E, C, D, and then let's put it off at the corner here, A and B. Topologically, that's exactly the same. Okay, and let's mark on the distances, and and just draw a tour that involves that. So I've drawn a tour there, obviously going along each edge twice, and I'm just trying to look at what might actually save some distance here. Now, looking at it, we can see the DH. In order to get from D to H, looking here, we're going all the way around the network here, or along here. So if I go directly from D to H, yes, it's 111, but it's going to save quite a bit, and we'll have to see whether that in itself is enough. If I go from D to H, I'm not bothering putting hours, by the way, in my tour, because it could be either way. So that, now, I've now still got a viable tour. Now it's come using that edge now. But what would the actual new lower bound be? So what's the upper bound, sorry. My improved upper bound would be, let's go back to blue. Would be the 806 I started with. Now I've added the edge DH, so that's plus 111, but I've taken away all of the edges. Now I'm going to rub all this out so I can see what the edges lengths are. I've taken all the edges away, so that's DC, which is 64, and CE, which is 59, and GE, which is 87, and was it GE? It was actually GF, which is 56. Let's just check again. Don't want to make a mistake. 111's been added. DC 64, that's correct. CE 59, that's correct. EF 61, that's correct. And GF 56, that's correct. Now I need GH has also been taken away, which is 38. So our new improved lower bound is, I seem to have missed an edge out again. I think I might have said it. Let's just do it one more time. I do apologise for this. 64, 59, FE 61, then GF, which is 56, then GH, which is 38, which gives a new upper bound of 639. Our target was 630, so we were close to doing it with that shortcut there. Now there are various options for the other shortcut, but I suppose the most obvious thing to do is to take these two edges by the away. And by the way, by the triangle inequality, if you're able to do this, then you will always be saving. You will always be cutting the journey. If ever you take two edges out for one, you'll always actually be reducing the value of your upper bound. So if we replace CA and CB with AB, that's here. Okay, then that is going to save us a little bit more. So let's just say that improved upper bound this time is equal to, let me get rid of question 3 so that we can get a bit more space before I move on. So the improved upper bound is the 639 that we had, plus, and that will be the edge that we are adding is our AB, which is 102. But we took AC and CB away, so let's take 57, take 68, and that equals to 616. Okay, and that will do it. Had that not done it, then there may have been other options, but thankfully we've gone to take it lower. I could have probably improved further by taking out AC and CE and then adding on AE, because remember that taking two edges away and adding it for another edge using triangle inequality will always decrease our upper bound, but we don't need to. We've done enough. Okay, so that's done. Okay, let's have a look. Oh, the question isn't answered because it wanted the tour. So we'll use this to, and I'm going to go around with my arrows here, but there are various options here. I'm going to go around, let's go around to A, B, to C. Oh, I can choose which way around this thing I'm going to go, but I'm going to go to D, to H, to G, to F, to E, to C, and then back to A. But there's many options. I could have gone reverse on either of those. I could just have gone, for example, A, C, E, F, G, H, D, C, B, A. I could have gone that way around. So there are various options there. Okay, so now that really is done for part C. Now it talks about the nearest neighbour algorithm, which is the other way of finding an upper bound. Right, so the nearest neighbour algorithm, that's basically if we're doing it from a network rather than a matrix, we just need to make sure that we start from our smallest edge. So we're starting at B. Okay, so we start at B. We go to our shortest edge, the closest place it can get to. So that's C. Okay, we then go to the next closest from there, which is A. And then we go to the next closest from that point, which is where we've got no choice. It's got to be E. We then go to the next closest that we haven't visited before, so that's got to be F. Then we go to the closest that we've been from here, which is G. It's a bit dodgy, this question. I'll tell you why in a minute. I don't quite know. It's a bit dodgy, but I'll tell you why. It's a bit surprised I'm doing this, but it was an exam question, so we better do it. Then we go to the next matrix, the next point, which is H. And then we go to the next, which is 111, because we can't go back to any of the vertices we've visited before. Then we go to the next one, which is back to where we started to, which was B. Okay. So that gives us another upper bound. I didn't actually add any of these as I went round. But I'll tell you why I think it's a bit dodgy in a minute, but let's just do it. BC is 68. CA is 57. AE is 98. EF is 56. FG is 38. GH is 111. Sometimes called a greedy algorithm here because all the short ones get taken, and then you sometimes end up with some pretty large ones at the end. And then DB is 108, which is 597. The reason why it's a little bit dodgy is, but it works here, and so I don't think it'd be a problem as far as the exam goes. But really, nearest neighbour algorithm being a greedy algorithm, doesn't really have any regard for the overall network. You're always looking at what's close to you. And because this is not a complete network, for example, A is not connected to B or whatever, there's no guarantee you using the nearest neighbor algorithm that we'd actually come up with a tool. We could end up with a dead end almost, because or it could get a little bit difficult because we're not connected to where we were at the start. So it's seems to me a little bit dodgy. But anyway, perhaps I'm wrong, but it seems to me that I've normally seen the nearest neighbor on the algorithm used on a complete network. But anyway, the question works. That's all we really care about. So hopefully we're all right. Now it says use it for length. By the way, we'll use this for part F, but this is the better upper bound than even the one with the shortcuts in it, because it's smaller. We want the upper bound to be as small as possible. Right, now we're going for the lower bound. Okay, so it says by deleting C and all of its arcs. We're going to delete all of these arcs, but then we're going to add on the two smallest from those. So this 57 and this 59 are going to get added to residual minimum spanning tree for the rest. Now I'm going to take advantage of the software that we've got by actually scrubbing these out, all the edges from C, and then adding these two later. You'll have to find your own way to actually make sure you can do this kind of without getting confused by edges that you include in or not. So we're just going to delete all of the edges from C, and then look at what the remaining minimum spanning tree from there. There you go. Well, unfortunately you can't do that in the exam, so you're going to have to find a way of looking through these, but hopefully this can explain how the method works. We're now looking for the minimum spanning tree for the remaining edges. Now, if we look at it, the minimum spanning tree, we're looking for the shortest one. So the minimum spanning tree, or residual minimum spanning tree, because we're actually taking it from the bits that are taken out, that's GF, which is 56. Right, to the next one will be FE, which is, oh no, I've missed out an edge. Oh, and I got that back again. That gives a total of 444. Okay, so that's the total of that, but that's of our minimum spanning tree. And if I go back to the other edges again now, I can see them clearly now. I'm now picking the smallest, because we deleted the edges from C. I'm picking the smallest other two. So that is 59 and 57. That's the two other ones from our smallest. So let's just make some room for that somewhere else, and I'll complete the lower bound. So this is my total for my residual minimum spanning tree total. So my lower bound is that amount, 444, for my minimum spanning tree, plus the two shortest edges from the C that I deleted, and they told us to delete C, and those two shortest edges are 59 and 57. So that comes to 560. Okay, total, let me write the 57 a bit neater, so 59 and 57, so that's 560. So we're nearly done with this question. It wants a range interval. Often our minimum spanning tree wants an inequality at the end. Right, now this one here, our upper bound, our best upper bound was 597 because it was the smallest. Doesn't ask that why, but they could in another exam say, why is this better? It's because it's smaller. But the best upper bound is the smallest one, so that's 597. Now the 597 is a viable tour, so it's possible that our optimum length that could be our best optimum length. So we definitely need equality to be a possibility on this side. Now, some confusion sometimes about whether we have a strict inequality or not. Now, examiner is normally generous here. We must have a non-strict, in other words, must have equality possible on this side, because what we've done with this here, or our nearest neighbour algorithm tour, is we found a viable tour, so we need it to be equal. Now, as I say, it's normally fairly generous as to whether we go this way or this way. In this case, really, because when we look at our actual network, that is definitely not, my lower bound is not a tour. We can see that it's getting dead ends. D is at a dead end, H is up at a dead end. So we know that that it actually can't be that. So we know that it should be a strict inequality. Now, I'm not sure, that's what the mark scheme says. I'm not sure whether a non-strict one would have worked here, would be accepted, but I do know that it's normally relatively generous with this. But because we've actually done it in a network here, and we can see it's not a tour, that should mean that we have a non-strict inequality here. Sorry, a strict inequality there. Okay, let's move on to next question. Question 3. Now, in some ways, when you have a traveling salesperson presented to you in the form of a complete matrix, life is much easier. It's much more straightforward, and we're not looking through edges in a network where, as you've just seen from my performance for question 2, it's easy to miss edges or whatever. So this should be more straightforward. Remember, the minimum spanning tree method for an upper bound involves finding a minimum spanning tree and doubling it. Now, they've told us to start at A, so we better start at A. You will be penalised if you don't. So let's number the 1 and cross out 1. Look for the shortest edge, so that's A, C, which is equal to 98. Okay, now I'm going to number the 2 up there, and then I'm going to cross out C, and I'm going to look for the smallest in either of these 2 columns. I've got 74s looking pretty small, 82, 104. It's looking like BC 74. So I'm going to number 3 on top of BC and cross out B. I'm now looking for the smallest edge along these 3 columns. That is looking like CD, that's 82. Cross out that D there and put a 4 on that. I'm now looking for the smallest in any of these last remaining numbers here, the smallest in column 1, 2, 3 or 4, and that is equal to CE, which is 103. Okay, now they total, so if I add all of those together, they total to 357. So my lower bound, this is part of A1, my lower bound, in this case we're doubling it because of upper bound. Oh dear, upper bound, we're doubling it. So that equals to 714. Okay, right, we need another matrix for the nearest neighbour algorithm method. We're going to start at A here as well. It tells us to. Let me move the matrix around so I've got a bit of space here. Do it over here. So this is now A2. Right, now here we're going to do it one here, and we look down the matrix and we're going to cross out A for the time being. Okay, now we're looking for the smallest here, which is AC. Okay, in this case I'm going to write it as a tour, so I'm not going to write the edges, but you can do it whichever way you want really. So AC, that will be equal to 98. And then we can put the next, we go to the next smallest here, cross out C, and then we go to number that one. But instead of looking down either column now, because it's a nearest neighbor algorithm, we'll choose that edge, we'll choose that here, so that gives me AC, and looking down for the smallest, ACB, so that's plus 74. Okay, notice I'm writing it as a tour, I'm not writing each individual edge. When we're doing prims or Kruskal's, write the edges. And you can write the edges too if you're doing the nearest neighbour, but I'd prefer to do it as a tour to emphasise the fact that we're actually trying to find a minimum tour. It actually is a tour that we work out, and we're going to end up back to where we started. Anyway, I probably shouldn't be waffling on because I'll lose track of what we're doing. We had B, we're going to cross out B, and now we're going to put a number 3 on B. We're now looking for the smallest one here, and that's D, which is 131. We cross out D, put a 4 on D, and now we're kind of forced to go for the 134. Again, well, it's often called a greedy algorithm because it has no, we don't look ahead to see what's coming around the corner. So it's 134 is that edge. Now here's the thing with, that's E, with the nearest neighbor algorithm, we've got to go back to where we started. So I'm going to number that 5 here. I'll put this in a different color here. We need to go back to where we start. Nearest neighbor algorithm. Must return to starting node. So that's 115 is our final bit. So even though we've crossed it out, you must not, we had to cross it out so that we didn't go back to A at any point, but we do need to return to A at the end. So you have to make sure you see that. So that's plus 115. So all of those added together give 552, which obviously is a better lower bound than the 714. Okay, so then that's part A1 done. Now we're looking for the lower bound using the matrix. So now this is part B, the lower bound. Okay, now it's told us by deleting E. So the smallest from E, by the way, let's have a look at that. That's A. Before I do that, smallest from E, the two smallest are AE, which is 103, and so AE, which was 115, and CE, which is 103. Okay, that's those two. And so now we're going to just take out those edges so that we're not looking at them. There we go. And now we're looking for the minimum spanning tree, or the residual minimum spanning tree for the other ones. I'm going to put my 1 on A. So we pick the smallest one, so that's CA, which is 98. Okay, that's the 98 here. So don't forget, we've got to cross out A, cross out C. So that's CA, that's 98. Put a 2 on the number C. Then look for the smallest. So that's BC, 74. Okay, BC, which is 74, cross out B. Cross out that and put a 3 there. And then the smallest is CD, which is 82. Okay, so the total for my residual minimum spanning tree is 254. Okay, so that's 254, but so that means my lower bound is equal to my 254, my residual minimum spanning tree, plus my 2 extra edges. I'm only bracketed them to distinguish in that between mine, because obviously it doesn't make any difference in terms of the calculation, but just to make it clear, these are my 2 smallest edges I've deleted, that I've taken from here. So that gives me a total of 472. Now, I'm not required to check whether that's a viable tour or not. So in this case, I'm going to cover myself and just say it could be equal to it as my lower bound. I'm talking about part C now to give our inequality bit. So optimum tour is greater than or equal to my lower bound in this case, because I have no idea whether these edges I've got here actually produce an optimum tour, and I'm not required to check if it does. So I'm going to cover myself and make it possibly equal to, and less than or equal to 552, because that's my upper bound, and that's the best one because it was smaller than the 714 I found from before. Okay, one more question and I think this tutorial is over. It's taken a bit longer than I thought it would do. These a little bit to be careful not to make errors like I've been doing, but hopefully we'll get there. So here we have a question where we've got an incomplete network. So in other words, not every edge is, and I've mentioned this before, I think in question 2, where not every edge is connected to any other edge. And we're kind of converting this to the more classical problem by finding a table of least distances. When we did this as practice in class, some of the people were a bit surprised we were asked to do this twice, but the reason was because we're using that matrix twice, and the examiner couldn't possibly give you a complete one, giving you a finished one without actually not testing the answers. So we've got the distance from A to B, we can see here is 35, not hard. That's directly in the matrix. So then the distance from A to E, well, we can see it's not direct from A to E, so we need to find the shortest distance, and I think it is those added up, is it? No, it is not the shortest distance, so we're looking for the shortest distance where 15 and 34. Is that the shortest? No, it is not. It's that distance there. That's 30. That's actually adding on 32 then to 15, so that's 47 from that one and that one. Okay. Right, now then we've got to add on CE. CE, well, that's nice and easy, it's direct. CE, and there's no quicker way. So CE, that's 34. And CE is 34 here. And we've got GD. GD, which is the most direct route, or the shortest route, I think, would be 32 to 21, which is equal to 53. And that is it. And we have to write it on both of these because we're going to work with both of these in the rest of the question, which is the only reason why you're asked to do it twice in this question. Okay, so I'm going to take a copy of those and we're going to then proceed with the question from there. So from this point onwards, we're not having to look at this network anymore. Although I can imagine in a question where they might ask you to actually write the actual route in the question that this refers to, but I don't think they have done here. So we're not going to need to look for that network again. Okay. So it's asking us for the nearest neighbor algorithm to start from A. So we better do that. Starting from A1, cross out A, look for the shortest one. So that's A, and looking for the shortest there, that's C. And that's going to add on 15. Okay, now I'm going to cross out C, put on the next, put a number 2 on the C. Now I'm going to look for the smallest down the column C. That's looking like 17, which is B. Okay, and I'm going to cross out B, put a 3 on B, and I'm going to look for the smallest now here, and that's equal to 38, D. I'm going to cross out D, put a 4 on D. Now I'm going to look for the smallest on D, and that's 11. That's E. Okay, and then I'm going to look out for, cross that out and put 5 there. And I'm going to then circle the smallest from there. That's 31, that's F. Now I'm going to look from the smallest from F, and I'm forced to choose G, which is 30, which is the last remaining one. And let's not forget to go back to A, so that's my 23 here. And they total to 165. Okay, so now we're doing the lower bound. So that's part B. Lower bound, they're telling us to delete A. Okay, so I'm going to note the smallest from A first of all. So that's AC, which is 15. And AG, which is 23. So that's the smallest edges from so that's 23. I'm going to scrub these out now. Scrub them out good and proper so you can't see them, but make sure that you've noted the 2 smallest. And now we can choose any of the edges for our residual minimum spanning tree. So I'm going to go to B first. So that's 1 on B. So the smallest from B is BC. So this is my residual minimum spanning tree now. So that's BC. which is 17. Cross out C, put I should cross out B from the start as well. Cross out C. So that's put a 2 on C, and now I'm looking for the smallest on either column. Looking at it, it's looking like CD, which is 21. Cross out D, put a 3 on D. Now I'm looking for the smallest down at either of these 3 columns. Looking at it, 34, we've got a 32 here, which I think is the smallest. That's C. G. No, of course not. It's 11. I hope by watching these videos you can see me my umming and ahhing, realising how careful you've got to be from with checking your smallest. So DE, which is 11, or maybe you're just going to be better than I am at it. Hopefully you will be. So that's DE, which is 11. Right, so now we cross out E and get 4. So then we're going to look at these, looking for the smallest. That looks like, now I'm being careful now, 31, let's check around, it is the 31. So that's EF, which is 31. Now I'm looking for the smallest remaining one from those, which is 30. That's GF, which is 30. So my total for my residual minimum spanning tree is equal to, those are all added together, is 110. Okay, but so my lower bound is equal to my 110, which is my residual minimum spanning tree, but I did record the 2 shortest edges. I can, I suppose, rub all that out again now. And we can see the 2 shortest that I did were 15 and 23. So it's plus 15 plus 23. That equals to 148. So that my answer lies within the range, but it hasn't asked for a range with in this question, so we don't need to do it. So that's it. It's taken a little bit longer, 48 minutes, to do a few questions. I hope you found that useful. It pretty well covers most aspects of the traveling salesperson problem you could be asked. I haven't really talked a lot about triangle inequality or whatever. I suppose what they could do here with this here is actually ask you to go back to this tour and see whether actually ACBDE, so AC, if you notice it actually ACB D doesn't go directly to D, so it goes indirectly, so it could actually ask you to write the actual route through the network, but it hasn't done here. So it's the only other thing I can imagine being asked. Okay, that's it.